Very good morning to everyone. Today, as a part of BPPK, we'll discuss about pharmacokinetic analysis of mathematical data. First, let us know what is mean by pharmacokinetics. In pharmacokinetics, we get absorption, distribution, metabolism, and excretion. Right? What is mean by absorption? If we take a drug, how it get absorbs into your body. What is mean by distribution? After we take a drug, it enters into the GI tract. From the GI tract, it need to be enter into the blood circulation. From the the entering of drug from the GI to blood circulation is known as absorption. From the blood circulation, when it is distributed to different organs present in our body, it is known as distribution. Metabolism. After drug enters into the organs, and in the organs, the drug is metabolized, means it is broken down. And after metabolism, the remaining, after showing its pharmacological activity, the drug will be excreted from our body. Then what is meant by mathematical data? Imagine, just little a story. Imagine the drug as a little tourist. Like keep a camera to the drug and send into your body. What will say? We can know how the drug enters into the body, where it goes, how much time it stays in that certain organism, certain organ, and how it excretes. Like a little tourist, like where you stay in the hotel, how much time you will stay, and when will you check out the hotel. In the same way, these parameters are calculated by using in statistical and mathematical equations. So, in the simple terminology, it is known as to analyze the drug concentration and to know the absorption, metabolism, distribution of a drug. We use mathematical equations. By using these mathematical equations, we can calculate certain parameters like maximum concentration. That is, what is the highest concentration of the drug in our body, and we can know the T maximum. Time to reach maximum concentration means how much the drug takes to reach its maximum concentration. AUC means area under the curve, total drug exposure in our body. By using mathematical equations, we can analyze the concentration time graph, the starting of a drug and elimination of a drug. The area in between is maximum concentration. The drug is exposed in our body, that is known as AUC, and half-life. How much time the drug takes to come it into the half concentration, and clearance, volume of distribution. These mathematical equations are with some hypothesis using some compartments which are hypothetical but not in the real. We take it in two major approaches, that is model approach and one is model independent approach. In model approach, we have again subdivisions of three. Compartment models, physiological model, distributed parameter model. Again, in the compartmental model, based on the arrangement of compartments, we have two. Mammillary and quaternary. As I told, this compartmental model is a hypothetical. For hypothesis, to make sure that that model represents the similar bodies and the organisms which are present, we mainly have some assumptions. Like in the models, we can't represent each and every model as a boxes. So we make sure that the organs which have same level of perfusions, like lungs, livers, heart, kidneys, they have equal amount of perfusion. Means the blood supply to these organs is similar. So we take that as a single compartment. and the organs which are less perfused, they are known as peripheral compartments. The main compartment comes with high perfusion organisms. Now you need to imagine this compartment consists of all the high perfused organs, and this compartment consists of low perfused tissues and organs. In this again, we have different types of based on the administrative techniques, we arrange indifferently. The drug movement between these two compartments, it follows first order. Like if the concentration is high, the perfusion and distribution is also high. And another hypothesis is, in every model, in every site, the drug distribution is equal. Like if you keep one particle in this drug, in every corner the distribution of drug is same. In the same way, the drug distribution to the lungs, kidneys, as they have same type of perfusion, the concentration in that organs is also same. And it follows first order kinetics. The drug distribution will be in two way. Means from central compartment to it goes to the peripheral compartment, and from peripheral to it comes to central compartment, then it will be excreted. If we see, one compartment, IV bolus, we need to represent, this is central compartment, from central compartment to peripheral compartment. And if we see the one compartment IV infusion, first the drug need to be absorbed. So in the central compartment, we do not have concentration at first, after infusion itself. So it takes time. First the drug enters into the central compartment, then it goes to the peripheral compartment. Then in return, again from peripheral compartment to the central compartment, then it will be excreted. In physiological model, we have perfusion limited, diffusion limited. Sorry, this is two compartment models. In single compartment IV bolus, we have only a single compartment, that is central compartment. In IV, it has directly drug in the first. In infusion, for the central compartment, the drug need to be absorbed, and from there it will be excreted. Here 1 represents the first compartment. 0 when it is in the blood, from the blood it enters into the first compartment, and from the first compartment it is excreted. So first let us know the applications. Why we need to use these mathematical models? First one is to know the drug behavior. Means we need to know where the drug stays, how much time it stays, and what are its characteristics. By doing this mathematical analysis, we can design different types of drug regimens. Means, and it also helps us to understand if there are any physiological changes in the body, will it affect the drug concentration. Means if a person is having renal failure, that person need to be given with same concentration and same dosages, or with the different dosages. This can be clearly analyzed by these compartmental models, and we can know the half-life and concentration, what are the toxic levels of this concentration, and where this concentration is, up to which type of tissues this drug is reaching in particular concentration. We can know all this. And when it comes to physiological model, there are some factors which affect the drug take in the physiological model. The rate of drug uptake into the tissue depends on mainly two things: the rate of blood flow to the tissue, and another one is the affinity towards the tissue, that protein binding or not. In physiological model, the blood flow rate limited model is, assume the drug is moving fast in the blood circulation, and then blood delivery to that organ is low. Means if we give a drug, the drug fastly moves in the blood circulation, but the organ doesn't get sufficient amount of blood in fast duration of time. That time we use this blood flow limited model. This type of the example of this drug is thiophenol. Means this drug moves fast in the blood circulation, but the point where the action need to be shown, that organ does not get the blood supply too fast. Here the rate limiting factor is blood flow, means that organ does not get the blood supply in an adequate. Membrane permeability rate limited model is another type in the physiological model. This is mainly used for the polar, non-ionized, or in the large molecules that cannot cross membrane easily. If the drug molecule is molecular weight is large, then the type of drugs will not easily perfused in the tissues. For that type of drugs, we use this type of model. It is mainly applicable for the hydrophilic drugs, and the rate limiting in this type of model in this the drugs are membrane diffuse. Then what is the advantages of this physiological model is we get it is so realistic to our body organisms. Unlike the compartment models, we do not describe in the boxes. Like we give the factors like blood perfusion, real type of organisms, real type of organ. It gives more accurate time and concentration profile in each organism. We can predict drug behavior in diseased conditions. If a person is diseased with, as I said before, like renal clearance or metabolic disorders, in this kind of situations, these physiological parameters, if there are any physiological changes in that person, will determine the physiological parameter changes using this model. Useful in the animal studies, tissue samples can be taken directly. Means now if we use the compartmental models, we cannot, there are some limitations to take those into animal parameters, but if you use physiological method, the animal parameters can be much accurate. Sir, ఇది ఊరికే పోతుంది సార్ వేరే slides. As I said before, in compartmental models, we take each box into the hyperfused tissues. In the same way, in the physiological model also, we classify tissues into groups and we figure out them. In that type of tissues which are rapidly equilibrium, means the tissues which get rapidly the concentration of a drug, we classify them, and the organs which come under this are lungs, liver, brain, and kidney. These organs consist of an high blood flow, so the distribution of a drug is also fast. And another one is slow equilibrating tissues. The slow drug in this organs, the drug is slowly distributed because the perfusion of the blood is very slow, like adipose tissue, muscle. Now let us compare what are the advantages and what are the benefits of compartmental model and physiological model. Compartment model is an hypothetical empirical approach to relate with real physiological or anatomical. Means there is some limitation to approach compartmental models into the physiological, but if we come to the physiological model, realistic approach, since it is based on the physiology and anatomy of the information. In compartmental models, we do not consider the natural physiology of the organ, but in physiological model, we mainly focuses on natural physiology of a human being or an animal by providing the organ environment, blood perfusion, and permeability in physiological model. In compartmental model, experimentally simple and flexible approach as far as data collection is concerned. In the compartmental models, we get large amount of data, and it is simple, and everyone preferred to go for compartmental models as it is flexible to be conducted. Physiological model is difficult, experimental, since exhaustive data collection is required. Means we need to collect vast amount of data in physiological. By collecting some amount of data, we cannot predict each and every parameter. For every parameter, we need to collect a vast amount of information for the physiological model. Data fitting is required for predicting drug concentration in a particular compartment. Now, if we want to fit the data in particular compartment in the compartmental model, we need to analyze a large amount of data used when there is little information about the tissue. If we want to find any new drug which we do not have vast information about the drug, and we do not know on which tissues it is going to act, we mostly prefer compartmental models. But if we have vast amount of knowledge and we know well about on which tissues and how the drug acts, we go for physiological model. Easy to monitor time, concentration, drug in the body with limited data. with less amount of data, we can predict the time concentration by using compartmental models. But exhaustive data is required to monitor time course of drug in the body. Means we need to spend lot of time and we need to collect lot of data if we use physiological model to understand the concentration and time graph. Mechanism of drug like absorption, metabolism, distribution, elimination cannot be explained by using these compartmental models. It is easy to explain drug absorption, metabolism, distribution, elimination mechanisms by using physiological models. Effect of pathological conditions on pharmacokinetic parameters cannot be determined. Like if there is any physiological change in the body, we cannot predict the difference in the absorption, metabolism, distribution by using the compartmental models, as we do not give that type of situations when we conduct compartment models. But in the physiological model, we can give such type of situations like kidney failure and metabolic disorders, which can affect the and we can know how it affects in the absorption, metabolism, and distribution. Frequent use of data, comparison of various drugs. Less common use it for data comparison. Now, if we want to compare the efficacy or pharmacokinetics of two different drugs or same drugs from different companies, it is better to go for compartmental models than compared to physiological model. Thank you.